Hello friends, welcome to engineering tutorial. So in today's video we are going to solve some questions on equivalent resistance. So we will solve some circuits and determine the equivalent resistance of the circuit. Okay, so here we have taken the first question. Okay, so this is a circuit here, as you can see. We have to determine the equivalent resistance across these 2 points x and y. So these kind of circuits can be a little bit confusing if you are a beginner to network theory or basic electrical engineering. Yes, you have solved these circuits in class 10th and also in 11th and 12th level, but still for a beginner to network theory or basic electrical engineering, these circuits can be a little bit tricky. So whenever you come across a circuit where you have to determine the equivalent resistance or equivalent capacitance or equivalent inductance, no matter what, always do not look at this circuit as a whole. Always try to separate it into different parts, just divide it and then analyze each part separately. And by the time you practice more and more questions on equivalent impedance, okay, equivalent resistance, inductance or capacitance, you will develop so much practice that just by looking at the circuit you can just determine what the equivalent resistance is. But if you are starting out with this part, so your approach should be to look at each part separately. So here in this question you can see that we can divide this entire circuit into 4 parts. The first part is this one, this 3 ohm and 6 ohm. The second part is the 1 ohm, 2 ohm and 5 ohm. The third part is this 2 ohm single resistance, and last is the 5 ohm. So let us analyze each part separately. Now if you look at these two resistors, 3 ohm and 6 ohm, this is 3 ohm and this is 6 ohm. Okay. Now if we connect a voltage source across it, and this is the total current, the current will get divided into, let's say, I1 and I2. It means that they are not in series, because in series the same current I would have flown through both the 3 ohm and the 6 ohm resistance. So it is not in series. Now if you see, these two resistors have their left ends connected at this point and the right ends connected at this common point, and both these points are connected across the voltage source. So it means that they are connected in parallel, and the voltage across both the 3 ohm and 6 ohm will be V. So it means the 3 ohm and 6 ohm resistances are connected in parallel. So what will be the equivalent resistance of only this combination, of only these two resistors? We know in case of parallel circuits, resistance is equal to 1 by 3 plus 1 by 6. Okay, 1 by 3 plus 1 by 6. We add the reciprocals. So it will be, let's say we take the LCM, be 18, this will be 6, this will be 3, this will be 9 by 18, by 1 by 2, okay, and the R equivalent would be 2 ohm. So for this combination the equivalent resistance is 2 ohm. Okay, so just remember that this is the R equivalent 1 is equal to 2 ohm for this. Next, let us consider these three. Okay, so let me just erase this part. Now this 1 ohm, 2 ohm okay, 1 ohm, this is 2 ohm, and this is the 5 ohm. If we connect a voltage source across this, here also let the total current be I, and the current will divide itself as, let us say, I1, I2 and I3. Means here also they are not connected in series because the current division is taking place at this point, and again this current will add itself up and it will flow. So here also the left ends of all the resistors 1 ohm, 2 ohm and 5 ohm, they are connected at one common point, and the right ends are connected at this point, and these 2 points are connected to the positive and negative terminals of the voltage source V. So it means that the 1 ohm, 2 ohm and 5 ohm are also connected in parallel. Okay. So the equivalent resistance of this combination, let us say 1 by R equivalent 2 is equal to 1 by 1, which means simply 1 plus 1 by 2 plus 1 by 5. The LCM is just simply the multiplication, just 10. So it will be 10 plus 5 plus 2. Okay, it will be 17 by 10, or the reciprocal will be R equivalent 2 be 10 by 17 ohm. Okay, so let's R equivalent 2 is equal to 10 by 17 ohm. Okay, so let me just remove this part. Now there is no need to analyze this 2 ohm because there is only a single resistor. So this part, the third part, R equivalent 3 will be simply 2 ohm, and this one 5 ohm is also a single resistor. There is no combination of resistances. So let us write R equivalent 4 as 5 ohm. So we have these 4 parts. Okay, we have calculated the resistances of the 4 parts that we divided our entire circuit into. Now across the terminals X, first we have R equivalent 1 equal to 2 ohm. Then we have this 1 ohm, 2 ohm and 5 ohm. The combination, the equivalent resistance of these 3 resistances, which we calculated as R equivalent 2 is equal to 10 by 17 ohm. Next, the 3 ohm and 6 ohm, we calculated their equivalent resistance as R equivalent 3 is equal to R equivalent 1 as 2 ohm. Okay, sorry, R equivalent 1, that was 2 ohm, and this is Y. Now these 3 are in series. You can see these 3 are in series. Why? Because if we connect them across a voltage source, let's say we connect them across a voltage source. Now just forget about this X and Y thing. The same current I will flow through each of the 3 resistances. It means that they are in series. Okay, this part, the equivalent resistance of these 3 resistors and these 2 resistors, they are in series. Okay, now this 5 ohm resistor is in parallel across these 3 resistances. Okay, because if we connect the voltage source here, okay, if we connect a voltage source here, the total current, let's say it's I, but will get divided. Let's say current I2 flows through this 5 ohm resistor and I1 will flows through the 2 ohm, 10 by 17 ohm and 2 ohm resistance. Okay, so it means current division is taking place. So the total circuit is, these three resistors are in parallel across the 5 ohm resistor. So first we have to add these three resistances, and then we have to find out the equivalent circuit considering the total resistance in 5 ohm as in parallel combination. So let's see. So we have to add 2 ohm, okay, plus 10 by 17 ohm plus 2 ohm, okay. So that will be, let's say, let us just use the calculator and convert it into decimal instead of doing all these things. Okay, 10 divided by 17 is equal to 0.58, so 2 plus 0.58 plus 2, so it is equal to 4.58 ohms, the total equivalent resistance of these three resistors. Okay, you can use the normal fraction approach and multiply and then calculate, but here to save time I use the calculator. The purpose is to make you understand how this thing works. Okay, so this entire resistance, okay, equivalent resistance of this part, okay, this part is 4.58 ohm, which involves the 2 ohm resistance, the 1 ohm, 2 ohm and 5 ohm resistance, and the 3 ohm and 6 ohm resistance. We calculated as 4.58 ohm. Now this 4.58 ohm is in parallel with 5 ohm. Okay, so let's see. The circuit now gets reduced to this. Four 4.58 ohm, and this is 5 ohm, X and Y. So now the resistance, equivalent resistance of this circuit is 1 by R equivalent is equal to 1 by 4.58 plus 1 by 5. Okay, so let us just calculate it. This is 0.218 plus this is 0.2, which is equal to 0.418. This is 1 by R equivalent. Do not write it as R equivalent because it will be wrong. So R equivalent will be 1 by 0.418, okay, which is 2.39 ohms, or we can write it as 2.4 ohms. So this is the total equivalent resistance of this entire circuit. Okay, so the approach here is that you divide the entire circuit into different parts instead of attacking the entire circuit as a whole. By that way you will get confused. So always divide the circuit into different parts, analyze each part separately and then combine them together. That should be your approach. And when you practice more and more questions on equivalent resistance, you will develop the habit, and just by looking at the circuit you can easily determine whether a group of resistors are connected in series or parallel, and how can we simplify the circuit in a very easy way. So this is the first question. Now let us take another one.